Hi, welcome to another lecture on business mathematics. Today we are going to continue our conversation about logarithmic functions. We are going to review what we talked about last time, plus we are going to look at logarithms as functions and draw their graphs and consider some equations involving logarithms. So you remember we started with the fact that we have learned about this exponentiation. 2 cubed is 8. If I want to ask 2 to what power will be 8, I use the logarithm as a way of phrasing my question. I say 3 is logarithm of 8 in base 2. So whenever we want to extract that exponent, the tool that we use is logarithm. It's written in the following way: if y is equal to b to power of x, and you want to extract this x, you say x is the logarithm of y in base b. What are our limitations here? B better be a positive number, otherwise we are going to be having problem with complex numbers and such. B better be a number other than 1, typically it's larger than 1. Otherwise 1 to power of x is always 1 and it wouldn't be interesting. Y always turns out to be a positive number, but x can be any number. So those are the issues of the domain and range. And then last time we talked about the wonderful properties of logarithms. Logarithm of a product, x times y, is a logarithm of x plus logarithm of y. Logarithm of a ratio is a logarithm of numerator minus logarithm of denominator. Logarithm of 1 turns out to be 0 because b to power of 0 is 1. Logarithm of a fraction that is 1 over x, or reciprocal of x, is minus the logarithm of denominator. We have two basic identities that says if you take a number, raise it to the power of logarithm of x in that number, you get the x back. And looking at it the other way around, if I'm taking logarithm of b to power of x, so b to power of x is my input to the logarithm. In base b, I get the x back. So these two identities indicate that if we go apply the logarithm and the exponential functions in succession, we go back where we were, meaning these two functions are inverses of each other. Then we add the power rule, logarithm of x to power of n. So here's my x to power of n. Becomes n times logarithm of x in base b. We also had short remarks on change of base. Any base, so long as it satisfies this, can be used. But what if you want to calculate logarithm of x in base b using some other base? Let's call it base c. Simple formula, it's going to turn out to be logarithm of x in base c and logarithm of b in base c. You have to divide them, and this is sometimes referred to as change of base formula. Among all bases, there is one base that stands out. It's so-called base of natural logarithm. There's 2.71828, which we said has root in business finance as well. In that case, logarithm base in this particular number is written in the following abbreviation, ln, which stands for natural logarithm. So if you have y as e to the power of x, you can write this as x is equal to the logarithm of y. These two convey the same fact. Okay, so that was a quick run of basic properties of logarithm. Now we are going to go ahead and take a look at some graphs of this function. So next item up, say graph y is equal to logarithm of x in base 2. Of course, a calculator or all sorts of websites will graph this thing for you, but we want to do it by hand so that we get a feel for what is actually happening. And to do that, we are going to go ahead look at cases where our x and y turn out to be friendly numbers, so that we don't get bogged down with all sorts of decimals and such. So first time we come across graphing problem, we make a table of our x and y pairs, and then go from there. So what are the easy numbers that we can calculate this thing by ourselves without using a calculator? Well, logarithm of 1 in base 2, or any base, what is that? Of course, logarithm of 1 in base 2 is 0. Let's review this thing. Logarithm of 1 in base 2 is 0 because what? Because 2 to the power of 0 is 1. 2 to the power of 0 is 1. So we are always extracting that exponent. What's the next easy number? Well, next easy number is 2. What's the logarithm of 2 in base 2? We are asking 2 raised to what exponent will be 2? Of course, 2 raised to the power of 1 is going to be 2. What's the next number? 4. What's the logarithm of 4 in base 2? We are asking 2 raised to what exponent will be 4? So the answer is, of course, 2. And next number is, of course, 8. What's the logarithm of 8 in base 2? Well, 2 raised to what exponent will be 8? The answer is, of course, 3. So on this side, I'm doubling every time. On this side, I'm increasing by 1 every time. This is doubling, and this is increasing by 1. What if I want to go backward? We don't go from 1 back to 0. Logarithm of 0 is not defined, or it's infinity. Let's just remind ourselves here. If I want to take a logarithm of any number, that number has to be positive. So I couldn't contemplate taking logarithm of 0, or if you insist, logarithm of 0 is going to be minus infinity. Let's see how. Before we get there, so we learned here that we are doubling. So when you go back up, every time you have to divide by 2. So 8 divided by 2 is 4, divided by 2, divided by 2 is 1, divided by 2 is going to be 1/2. What's a logarithm of 1/2 in base 2? So 2 raised to the power of what number will be 1/2? Of course, the answer is -1. So as same trend as here. If you double, you increase. If you divide by 2, you subtract 1. So I divide by 2. Next number is 1/4. What's the logarithm of that? It's going to be -2. And how about 1/8? It's going to be -3 by the same reasoning. So once we have all of these, we can easily graph our let me erase these so that we are ready to for graphing. So I have my here's my y-axis, here's going to be my x-axis. So I'm going as far as 8, so let's consider this thing 8, and then half of that will be, let's around here, 4, half of that around here is 2, half of that around here is going to be 1, half of that will be 1/2, and after that things get crowded, so 1/4, and next is 1/8, and so on. So here I have 1, 2, and 3, and then of course -1, -2, -3. Now what? Let's go graph this 1 and 0. That's here. So that's going to be the x-intercept of logarithm. It's at point 1 on the x-axis. 2 and 1, so that's going to be here. 4 and 2, 4 and 2 will be here. 8 and 3, 8 and 3 will be somewhere up here. So this was 2 and 1, 4 and 2, 8 and 3. So you can imagine if I go further out here, I go to 16, I go up by 1 to go 4. So On x-axis I am going very fast every time doubling, but on the y-axis I'm going up very slowly, so a snail-like increase while this is running. Okay, at 1/2 we said we are going to be at 1/2, we are at -1, and 1/4 we are at -2, so that's going to be a quarter 2, and that was 1/2 and -1. And next is going to be 1/8 and -3. So these are my points. Now I connect them, so maybe I use a different color, say connect them with blue. This is the graph of y is equal to logarithm of x in base 2. If I was looking at base 3, I would do the same thing, except that the numbers I choose here will be 1, 3, 9, 27, and so on, 1/3, 1/9, 1/27, and so on. That's going to make this point to go further out, and that's going to make this blue curve more flat, so it's going to travel here instead of up there, and then similar style. And this is going to get bunched up closer to the y-axis. Okay, so once you see one of these logarithms, you have essentially seen all of them. The logarithm of x in base b for any b larger than 1 looks kind of like this. Okay, so let's record what we see here. We have seen the x-intercept. Let me write in white. X-intercept is at 1. This is the x-intercept. We notice our graph is increasing all the time. That means as we go from left to right, we go up. We notice that the domain of this is all numbers that are positive. However, the range is all these numbers. Nothing is missing from them. The range is the whole gamut of numbers from -infinity to infinity. As we approach x equal to 0, we are descending here, and that creates a so-called vertical asymptote. A vertical asymptote is a line that comes very close to your curve as you go far away from the origin. So here we have the y-axis, which is x equal to 0 itself, x equal to 0, or y-axis is a vertical asymptote. And sometimes in your business classes, they are going to emphasize that this looks like a cup that has been turned upside down, and the curvature of it is under it, and so on. So these are some basic properties of logarithm of x in base 2. Now you might come across a problem where some of these ingredients are changed a little bit. For example, what if I have logarithm of x minus 3 in base 2? What does that do? You can make a table as before and try to hunt for friendly numbers. Another way is to come up with a short description of what will happen. What is the influence of this 3 in our picture? Perhaps we go ahead and graph this thing from scratch first time around, and then we come up with a short description of how can you quickly answer this thing without creating everything from scratch all over again. Okay, so we are going to make this table from scratch, and then we graph. So our friendly numbers, whatever you're feeding to logarithm, well, our very first friendly number here was 1, which led to a 0. Well, when would this become 1? Well, of course, x has to be 4. If x is 4, once you subtract 3 from it, you have 1, and logarithm of 1 in base 2, we don't need a calculator, we get that. Next, I need this input to be 2, because my next friendly input was 2. Logarithm of 2, I know it's 1, I don't need a calculator to figure that out. So I ask myself, when does this become 2? Of course, my x has to become 5. If x is 5 and the x minus 3 is 2, and logarithm of 2 in base 2 is 1, and so on. Next, when is this going to be 4? Of course, x has to be 7, and then I'll have 2 as the output. And next, x has to be 11, so that when we subtract 3 from it, we get 8, and logarithm of that is going to be 3. So next number up is 11 at time we get 3. Okay, now notice that these are not doubling as nicely as they were doing here, because they're all kicked around. So next number for me is, when does this thing becomes 1/2? Of course, it has to be at 3.5. So 3.5, or 3.5, or if you wish, 7/2. If you subtract 3 from this thing, you get 1/2, and logarithm of that will become -1, and so on. So let's go ahead and draw this picture. So where is our x-intercept now? Our x-intercept is happening at 4. So if this is 1, 2, 3, and 4, I get my x-intercept. Next number is 5. At 5, I get 1. At 7, so 6, I don't have an easy number there, but 7 is my next number. I get 2, and then 7, 8, 9, 10, 11. I was hoping that I wouldn't go out of bounds. And then here we come up one notch and we get to 3. Everything that was happening here between 1 and 0 is going to get compressed between 4 and 3. That is, at 3.5, I'll be at -1. At 3.25, I'll be at -2. 3.8, I will be at -3, and so on. So if I connect all of these points, what do I get? Something like this. This graph of logarithm of x minus 3 in base 2. We notice everything shifted to the right by 3 units. That is, all these points 2, 4, 8 got shifted to everything got shifted to the right by 3 units. And interesting fact is that the same thing happens to our vertical asymptote, that wall that was holding the logarithm to the right side of it. This is it, x equal to 3. That is essentially the wall that pushed everything to the right. So this is the 3 here indicates how far to move to the right by. Move to the right by 3 units. And once you have the graph of logarithm, by this idea, you can easily, quickly graph this, and these are covered under the ideas of translation in your textbooks. Okay, next up, so we learned a little bit about graphing. Next up, we are going to go ahead and take a look at some equations. Now, let's go ahead take a look at some logarithmic equation. This means equations that have logarithm in them. So for example, here's a case of a simple logarithmic equation. I have logarithm of x minus 2 in base 2, or in any base, it doesn't matter what base we have, plus logarithm of x minus 3 in the same base is equal to the logarithm of 2 in that same base. What we want to find here is what is x. B could be any number that's acceptable as a base. So what do we do in this case? We apply rules of logarithm to collect it in terms of single log on both sides, and then the problem will be straightforward after that. So what we have? Logarithm of something plus logarithm of something else. Sorry for that. Logarithm of x plus logarithm of y is logarithm of x times y. So we are going to use this to say the left hand side can be written as a single log. We simply have to multiply these two, x minus 2 and x minus 3. On the right hand side, I don't have any simplification to do. As it is, it's good. Logarithm of two numbers in the same bases are the same if the two numbers are the same. So this has to be identical to that for the logarithm to be equal. So at this point, we say x minus 2 times x minus 3 is equal to 2. I multiply, this becomes x squared minus 3x minus 2x plus 6 is equal to 2. I collect my x's, x squared, this is minus 5x. Subtracting 2 from 6 gives me a 4. Then I can factor this thing. If I couldn't, I'll just use the quadratic formula. So x minus 1 times x minus 4 equal to 0. This gives me two answers. X can be 1 and x can be 4. Now, x equal to 1, if I put it in my original equation, I'll have 1 minus 2, which is negative 1. 1 minus 3 is negative 2. And we said logarithm's input has to be positive. Let me remind you again here. When you take logarithm of a number, that number has to be positive. Because when you exponentiate, you always get a positive number. So the input of a logarithm has to be positive. And here what we have is x is not acceptable because if you go back then you're taking logarithm of a negative number, so this falls out. This becomes not acceptable. We have to flag that out. X equal to 4 is the only solution. Logarithm of 4 minus 2 is going to be 2. 4 minus 3 is 1. Logarithm of 1 is 0. Logarithm of 2 in base b, that's of course logarithm of 2 in base b. This is our solution, so we box this, that this is our final solution. We flag that. The other one is a so-called extraneous number. It doesn't fit the original description. The reason it creeps in is that this negative and that negative, when you multiply them, becomes positive. It looks like it's acceptable, but in fact it is not. Okay, so that was a basic review of some simple facts about the logarithm. We learned how the graph looks like, and we also have a basic review of the logarithmic function. So remember, you can always graph patiently, just find the points and put them on a picture. We have ideas about translation that makes graphing quicker, so long as you remember a long list of possible things you can do to the graph of a function. For solving logarithmic equations, use the rules of logarithm to put everything on the left and right to the same base, single number to the same base, and then set the numbers equal to each other. And then at the very end, check to see that what you got is actually acceptable and that it does not make the input of any of the original elements of the problem, input of logarithm, to be negative. So those have to be ruled out. Okay, until next time, good luck and God bless.